For the audio recordings, I will be going into further detail on some of the more important concepts from the slides and helping to provide further explanations for these concepts. One of the main points from this chapter is the importance of scientific approaches to observation, and this quote does a good job of explaining why it's so important and how we approach particularly experimental observations. This is from Kurt Lewin, and it says if you want to understand something, try to change it. And this is really the approach we take when we're using the experimental method. So an experiment has two important points, an independent and a dependent variable. In scientific observation and an experiment in particular, we're changing one thing to see how it affects the other. The independent variable is the factor that we are changing or manipulating. It's something that we believe is the cause of something. The dependent variable is the measured variable or the outcome or the behavior that you're interested in changing. You can think about this in a couple of ways. One way to think about it is the independent variable as the thing that's manipulated, or the independent variable as the cause, and the dependent variable as the effect. So for example, I might believe that reading your textbook improves test scores. So I might manipulate whether or not students read their textbook and have one group read a textbook and one group not read a textbook, and see how that affects test scores. So the thing I'm manipulating is the independent variable. That would be reading of the textbook. The thing I'm measuring or the outcome is the dependent variable or test scores. Now, because the independent variable is the factor that I'm manipulating, I'm going to have different versions of the independent variable. These are called levels of an independent variable. So at the most simplest experiment, we could have two levels of an independent variable. The independent variable is either present or absent. So in the textbook example, one student gets the independent variable, one student or one group of students reads their textbook, another student or group of students do not read their textbook, therefore the independent variable is absent. This is also often referred to as the treatment and the control condition, where the treatment condition or the treatment level gets the independent variable. The control condition, or the control group, tells us about the behavior, what happens without the treatment or without the independent variable. We need this control condition to have a comparison group, and that's the importance of that. Another really important idea that we'll be coming back to throughout the semester is that of constructs. Constructs are a concept or idea in psychology that we use to explain behavior or mental processes. Concepts are really crucial to kind of understanding because these are the basic things that we talk about in our psychology class. Things like aggression, depression, emotion, intelligence. These are kind of the basic ideas of psychology. The issue is that we can't directly test these things. So if I asked you to define happiness, how would you define it? It would probably be a little tricky for you to come up with a very clear definition. This is because happiness is a construct. It's an idea that we have. We believe this thing exists, but we don't have an easy way to measure it. This is something we constantly grapple with in research. But the way we've come up with measuring it is what's called an operational definition. An operational definition is how we measure a construct in a specific study. It's some kind of observable procedure used to measure a construct. It's important to remember, though, that these operational definitions will vary from study to study. So to further define a construct is something that we think is real, like happiness. However, it's intangible. We can't touch it, we can't see it, we can't physically feel it. But in psychology, often these are the kinds of things that we want to try to measure. So for example, maybe we are interested in studying sexual jealousy. We think that exists. We've seen people exhibit things that show signs of sexual jealousy, but it really can't physically be touched or felt or seen. What we need to do when we go to study it is we have to decide how we're going to measure it, and that's our operational definition. So we could operationally define sexual jealousy in terms of responses to some kind of hypothetical situation involving infidelity. We could look at heart rate in response to these situations or angry facial expressions. But the important thing to note is we could look at any of these things and they would all be equally good operational definitions. So how we operationally define a construct is going to vary from study to study, and it could lead to different results. So the good thing to study with constructs, or to remember, is that a construct is kind of the general phenomenon. If somebody asks you what your study was about, you say happiness, depression, those kind of general ideas that we study in psychology, and an operational definition is how you actually measure it. Another important component of making good observations is making good predictions. And it's really important to make these good predictions before you do your study. So these predictions we call hypotheses. And scientific hypotheses need to be testable. And they also need to be a tentative explanation for something. They need to explain why the phenomenon is happening, how it's happening, and be a clearly stated prediction. It also needs to include the constructs and how they are defined and measured. So like I said, the hypothesis is the basis of your research. So a hypothesis must be testable because that is the point of your research. There are three things that make a hypothesis not testable. The first is that you haven't defined your construct or explained how you're going to measure it. The second is that it's circular. So an event itself is used as an explanation for the event. So shy children have bad peer relationships because shy children are often alone. This is a circular explanation because being often alone is part of the definition of being shy. Final component that makes a hypothesis not tested is if it appeals to ideas or forces not recognized by science. People are controlled by the devil is not a good explanation or a good hypothesis. Another important component that students often miss is that in order for it to be a hypothesis, it must be directional. It must explain how things are going to be related. Your hypothesis cannot just be that reading the textbook will be related to your test scores. You need to explain how they're related. So that kind of hypothesis would be something along the lines of, it's expected that students who read the textbook more or who read the textbook compared to students who don't read the textbook are more likely to do better on the test. You can see I've stated it as a prediction or an explanation, and I've stated the direction and how I expect my constructs to be related. So far, I've been focusing mostly on experimental work. However, there are also other types of studies in which we cannot or do not manipulate something, and these are called correlational studies. These are mostly useful for prediction. So a correlation is a measure of how two constructs from the same people vary together or go together. So how much two things move together. And these are really helpful for making predictions. So we can think about things like attendance and GPA. You'd expect that students who attend class more regularly will have a higher GPA. We'd expect those to move together quite frequently and therefore have a strong correlation. In contrast, if we think about things like shoe size and GPA, we would probably expect that those two things would be independent of each other, and therefore they would not have a strong correlation. So correlation can be really useful in helping us predict how relationships might be, but it's really important to remember that correlations don't explain why there's a relationship between variables. All they do is test whether the two variables are related. This is where the experiments come into play, because experiments help us identify causes of behavior. So with the experiments, we're manipulating one factor, the independent variable, to see how it affects the dependent variable, or the second factor. So that gives us experimental control. In contrast, with correlational studies, we're measuring two things and looking at how they're related, but we are not doing anything to change the variables. With a correlation, all we do is measure the two variables and test whether they're related. In order to have a very good explanation of behavior, we need causal inference. So this is the goal of experiments. We want to be able to state that one factor causes another event or a behavior. So we want to be able to say that X caused Y. there are three conditions that we need to have met in order to be able to say this. The first is that the events are correlated, or they covariate, or they change together. The second is that there's a time-order relationship. If we think that X causes Y, you have to have experienced X before we see the change in Y. The third is that you've eliminated alternative possible causes. Nothing else can be causing the problem. So let me give you an example. Maybe I think that taking Advil makes a headache better. The first thing I'd want to do would see whether there's a covariation of events. So the more I take Advil, the less headache I have. If I don't take Advil, then I do still have a headache. We also need the time-varying or time-ordered relationship. So in order to say that the Advil causes the headache to go away, I have to have taken the Advil before my headache goes away. If the headache goes away first and then I take the Advil, obviously the Advil is not causing the change in the headache. And finally, we have to eliminate possible alternative causes. I took my Advil with a glass of water. Maybe it's actually the water that's making my headache better, not the Advil. So I need to add another condition where I had one person who takes Advil and water, one person who just takes water, and one person who does nothing, or something along those lines to eliminate the possible alternative. And it's a pretty common mistake that you see in research where they haven't met all of these criteria before they make causal. So correlational studies have only met the first criteria. They have just measured two variables, seen that they relate, but typically those variables are measured at the same time, so you don't have the time-order relationship, and you haven't eliminated other causes. So this is one example of how correlation does not equal causation. So this is a measure of the housing price index, the price of houses, and also the black line is a measure of the number of babies named Ava. And then you can see the title at the top says, did Ava cause the housing bubble? Because what you can see is there's a high correlation between the housing price index and the babies named Ava. Both peaked in 2008 and then declined in 2009. So with this correlation, we need to ask the question, did the babies named Ava cause the housing bubble? I think the logical answer is no. And it just really highlights how it's important to remember that correlation does not necessarily mean that one thing caused another. Likewise, we can't say with certainty that the housing price index caused parents to name their babies Ava. It's possible that something altogether caused both of these factors. Another main issue in experimental research is looking out for confounding variables. Confounding variables is when two independent variables change or covary together. What this means is if you have two independent variables changing together, we can never be sure which of those two is causing the effect on the dependent variable. So to establish causal inference, we have to get rid of these confounding variables. Let me give you an example. Let's say we're interested in whether tutoring can improve children's social and emotional skills, as well as their academic skills. And we have two groups of children. One group stays after school twice a week and gets tutoring. The other group goes home and stays alone by themselves after school. Now we have this problem where children who get tutoring actually get two things. So they get academic tutoring, but they also are in the company of an adult. So there's two potential independent variables which could be causing a change in social functioning. So if we find that the tutoring group does in fact have better social functioning, it may in fact be that tutoring helps social functioning, but it may just be that having more opportunities for interaction also helps social functioning. So this is a confounding variable. In order to really establish that tutoring itself causes children to have better social abilities, we need to tease apart those two variables. The way we do this is add another group. So we might do something like have three groups. Have one group that gets tutoring, one group that gets to informally hang out with another adult, and then a third group that just goes straight home. If we find that both the tutoring group and the hanging out group both have better social skills, what that tells us is it appears that just spending time with an adult improves social skills, and there's nothing specific to tutoring that helps. In contrast, if we find that the tutoring group does better than either of the other two groups, then we can really say that it was the tutoring in particular, that's the independent variable, that caused the change in the dependent variable.